Hello and welcome back. Okay, so we're doing something a little interesting today. It's called vector valued functions. We can do derivatives with vector valued functions, and we can determine a particular solution given a rate vector and initial condition. But first we have to figure out, what is a vector valued function? In this lesson and in the next, we're going to explore the vector form of parametric equations. At first glance, parametric equations and vector valued functions look to be almost identical. And honestly, we kind of treat them identically. The main difference, though, is the range. Parametric equations, each individual t produces a point, and the graph is the string of all those points. For vector valued functions, each individual t value produces a vector. And the graph of the vector valued function is the string of all the terminal points of the vectors. In 2 dimensions, a vector valued function can be represented in, well, a couple different forms. The first form here, r of t, this is called component, like component notation, or we're using component factors. And we'd say r of t, and we have this like bold R, but like if you're writing it on a piece of paper, it's hard to make a bold R. So in context, we'll be able to see that just R of t. And then we've got these like vector brackets. And then notice that in the x spot, well, it's the x parametric function. And in the y spot is the y parametric function. And then the other version of this is, we call this unit vectors. And it's the same thing. It's just that we've got the x parametric function followed by this I plus the y parametric function followed by the j. And we don't use that as much in calculus. Maybe that's more of a physics thing. But good to know and to be able to use both of them. Unless otherwise stated, the domain of a vector valued function is considered to be the intersection of the domains of the component functions f and g. Example 1. Express the parametric functions x equals 2 cosine t and y equals t plus sine t as a vector valued function. Okay, this is really not that bad. Component factors, well, you just plug it into these little vector brackets. And the x parametric equation goes first, and the y parametric equation is second. If you want to do unit vectors, then we've got the x component followed by an I plus the y component followed by a j. Example 2, given the vector equation t squared plus 1i and ln 2 minus tj, find the following. Okay, well, first we need to identify the x parametric function. Well, that's just the first guy. And the y parametric function, that's just the second guy in front of the j. So we've done that. Now find the domain of r. Okay, well, the domain of t squared plus 1 is all reals. We don't have any limitations on that. The domain of the y component, well, 2 minus t has to be greater than 0, which means that t has to be less than 2. So the intersection of these is negative infinity to 2. So our vector equation has negative infinity to 2 as its domain. Example 3. Sketch the plane curve represented by 3 cosine t, comma 4 sine t between 0 and 2 pi. We're going to use arrows to indicate the direction the curve goes and then write the rectangular equation. I think you're going to find that this is pretty much just like graphing a parametric set of equations. So let's start with just a simple t, x, y table to see what's going on. So if you plug in 0 to our x component, you get 3. If you plug in 0 to our y component, you get 0. If you plug in pi over 2, you get 0 and 4. And notice I'm plotting these as I go. If you plug in pi, you've got -3 and 0. And if you plug in 3 pi over 2, we've got 0, -4. So we'll connect those dots and look at, we have an ellipse. But we do want to indicate the direction the curve went as we were plotting it through time. Now, to write the rectangular equation, you've actually seen this before. So if we have x equals 3 cosine t and y equals 4 sine t, our goal is to eliminate this parameter t. So to do that, we'll divide by the constants in front of them. So we get x over 3 equals cosine t, y over 4 equals sine t, and then we get to do this cool math magic where we square both of them. Do you remember doing this? So if we take the x component squared and we take the y component squared and we add them together, we know that cosine squared plus sine squared equals 1. Therefore, we know that x squared over 9 plus y squared over 16 also equals 1. And there we have the equation of our ellipse. We can do a lot with vector-valued functions. Many techniques and definition used in the calculus of real-valued functions can be applied also to vector-valued functions. We can add them together. If we have two vector functions being added together, that means we just add their x components and we add their y components. Scalar multiplication. If you have a vector function multiplied by some constant, you just multiply the x component by the same constant and the y component by the same constant. With limits, the limit as t approaches a of a vector valued function, you just take the limit as t approaches a of the x component and the limit as t approaches a of the y component. And guess what we do with derivatives? Derivative of the x component and derivative of the y component. So like before, you just get two problems in one. We can do motion along a curve with vectors, which we actually started talking about just a little bit in the last lesson. We would start with a position vector. R of t equals x of t comma y of t. To get a velocity vector, guess what you do? Just take the first derivative. X prime of t and y prime of t. Any guesses on the acceleration vector? We now have the double derivative of the x component and the double derivative of the y component. And then speed, oh, this is what we did in the last lesson. We learned how to take the speed of a vector function, and we also learned that arc length was the integration of speed over a particular interval. So here we have a particle moving in the xy plane so that any time t greater than 0, the position of the particle is given by an x component and a y component. So find the velocity vector when t equals 1. Okay, we'll just take the derivative of the x component, stick it in the x spot, and the derivative of the y component and stick it in the y spot. And then just put these vector brackets on the outside, and there we have a velocity vector. Now, specifically, we wanted it when t equaled 1. So if we plug in 1 to both the x component and the y component, now we have our velocity at 1 of 11 and 1. And then the acceleration vector is just going to be the same process. We'll take the derivative of the x component of the velocity and the y component of velocity, and then plug in 2 to find our acceleration vector at 2. Okay, new particle moving in the xy plane, and at any time t greater than 0, the The position of the particle is given by, of course, an x component and a y component. Find the magnitude of the velocity vector when t equals 1. What does that mean? Basically, what it is it's the distance formula. Instead of a distance traveled on the curve, this is going to be your displacement. So there's no need to integrate it. We're literally just putting the derivative of the x component, squaring it, the derivative of the y component, squaring it, adding them together, and taking the square root. So at time t equals 1, we've got the square root of 25 plus 9, or the square root of 34. Example 6. A particle moves in the xy plane. We have an x component of root 3 minus 4 cosine t, and a y component of 1 minus 2 sine t. Now the path of the particle intersects the x-axis twice between 0 and 2 pi. And we want to write an expression that represents the distance traveled by the particle between the two x-intercepts. Wow. Okay, well, what we know is the path of the particle is going to intersect the x-axis at the points where the y component is equal to 0. Okay, well, that makes sense. So we'll set our y component equal to 0 and solve. So sine t equals 1/2, which gives us 2 zeros of pi over 6 and 5 pi over 6. So if we're going to find the distance the particle traveled, or the arc length between those two zeros, then we just have to integrate our speed over that interval. So let's see, we need the derivative of the x component and the derivative of the y component to plug into that. And it just asked us to write an expression, so we don't actually have to solve that. Example 7. Point P moves in the xy plane in such a way that the derivative of the x component is 1 over t plus 1, and the derivative of the y component is 2t for all t greater than 0. Find the coordinates of P in terms of t, given that when t equals 1, x equals the natural log of 2 and y equals 0. What does that mean? Well, basically, we have been given a velocity vector. And we want to find the position vector given those conditions. Well, to go from velocity to position, we can do that. That's just integration. So we'll take our x component, take the antiderivative of that, so we get ln of the absolute value of t plus 1, and of course, plus our constant of integration. And we have an initial condition, x equals ln 2 at t equals 1. So we'll plug in 1 for t, set that equal to ln of 2. Okay, c equals 0. Let's clean this up. Therefore, our x component for the position vector is ln of t plus 1. Now we'll do the same thing for our y component. So we'll take the antiderivative of 2t. We get t squared plus c. And we'll take our initial condition, so y equals 0 at t equals 1. So we get a c of -1, and a position vector for y, t squared minus 1. So now all we have to do is put that into a point with our newfound x component and our newfound y component. Part B says, write an equation expressing y in terms of x. Well, we've actually done this before too. We just have to figure out how to eliminate the parameter t. We already know that our x is ln of t plus 1, so let's solve for t. We can exponentiate both sides, subtract 1, and we get t equals e to the x minus 1. Now our y component is y equals t squared minus 1. So we'll take our t, plug it in. There we have it, an equation expressing y in terms of x. Part C says, find the average rate of change of y with respect to x as t varies from 0 to 4. Oh my goodness, what does that mean? Well, basically, it's a slope, change in y over change in x. We're going from 0 to 4, so we've got y of 4 minus y of 0 over x of 4 minus x of 0. 15 minus negative 1 over ln of 5 minus ln of 1. And there we have the average rate of change. Part D, find the instantaneous rate of change of y with respect to x when t equals 1. So we're looking for dy dx when t equals 1. So that's going to be dy dt over dx dt. So 2t over 1 over t plus 1. Plug in 1 and you get 4. A lot of stuff, once again, that you've done before, but just looking at it from the vector valued perspective. Thanks for being here, and I'll see you next time when we start a new adventure.